So, this is the fourth class where we continue our journey with fiber laser. Let me briefly summarize the what we learned in the last class with regard to the pumping of a fiber laser and its subsequent glazing. Like any other solid state laser, fiber lasers too are optically pumped. Although the very first fiber laser operated in 1961 did make use of side pumping, but the long strand like shape makes this laser unsuitable for pumping through the site. So side pumping is not a suitable option. So it has to be essentially pumped through its end. Now the end is absolutely narrow. Its area is because its diameter is it's like human hair, the glass tracks. So end pumping is also challenging. But if it has to be pumped, it has to be pumped through the end, not through the sides. That was for sure. So the difficulty of coupling the divergent light emitted by a conventional source to the tiny end of the fiber was primarily responsible that why fiber laser did not gain any much attention during 1970s, 1960s, and even major part of 1980s. The advent of dart lasers in the 1980s offered the prospect of transporting light efficiently to the end of a fiber and led to the resurgence of interest in the research on fiber lasers. And there has been no stoppage thereafter, and these lasers have now exploded out of the laboratory into the numerous applications profoundly impacting humankind. For end pumping to be effective, the light must enter the core of the fiber within its acceptance angle. We now know it. A requirement impossible to be met by conventional lamps or light emitting diodes or even conventional lasers. These sources usually emit are usually much too large. The source itself is much too large, and its the area over which it emits is also much too big, and emit into an angle that is too wide to allow any meaningful coupling of the light into the fiber core. The dart laser, on the other hand, emits from a tiny area. The semiconductor laser is also tiny, as small as the fiber itself. Therefore, it actually fits well as far as end pumping of the fiber is concerned. And it emits into a much narrower angle that can be effectively transported in the fiber core to its end. And once inside, the pump light, as we know, will be guided through the length of the core by the phenomena of total internal reflection. And if it can be put through its acceptance angle, then the entire beam will be very well guided down the core of the fiber. And if for a dart laser of appropriate wavelength, the light will be gradually absorbed by the doped species as it travels down the fiber. When you choose the wavelength appropriately, that means you have these are your energy levels. This is the upper laser level, lower laser level. This is ground level, and this is the pump level. So your semiconductor dart laser must operate at a wavelength which fits the energy of the photon fits exactly between the ground and the pump level. So as this light beam traverses down the core of the fiber, it will be gradually absorbed by the doped species, which will be excited and eventually emit your light through this transition at a wavelength, say lambda L, and lambda L is of course more than lambda P. And we must actually, for sake of completeness, we must represent lambda L as blue, just to indicate that its wavelength is, sorry, I'm extremely sorry, lambda p to this is lambda L, that lambda L is more than lambda P. All right. So then how will be the experimental system? Let us explore it. So like any other laser, the onset of lasing in an active fiber also requires cavity. You must have a cavity. You know it now very well, that laser is nothing but an integration between cavity and an population imparted medium in which you have established gain. A very simple fiber laser cavity configuration along with the end pumping arrangements from both sides is shown here schematically. The emission from a diode laser. Let us first consider pumping through one end. So this is a diode laser. The output of the diode laser, emission from a diode laser, is appropriately focused. This is the focusing lens, and then launched into the fiber through its acceptance angle. This angle is its acceptance angle. Otherwise, pumping will be inefficient. Launched into the fiber by means of a suitably located dichroic mirror. So this is a dichroic mirror. So the pump wavelength is, this is the pump wavelength, lambda p. This dichroic mirror is such that this is the mirror. So you shine it with the wavelength lambda p. It is reflected. So lambda p is reflected, and then it is coupled into the fiber, one end of the fiber. This is lambda p. And then it offers high reflection at the pump wavelength and high transmission at the lasing wavelength. So if the laser light falls into it, suppose this is laser light that falls at an wavelength of lambda L, then it will be transmitted. Lambda L. We come to this in a while. So then this dichroic mirror actually reflects this focused beam of light that is emitted by a diode laser. Diode laser is this somewhere here. Diode laser, and it couples into the fiber through its end within its acceptance angle. The pump and the laser beams are indicated, this pump is indicated in green and laser beam is indicated in red respectively, to underscore the fact that lasing always occurs at a wavelength longer than the pump. So as this pump beam travels down this core, the core will of course have the, these are the light emitting species. So as the light travels through this, they will absorb this light at wavelength lambda p. For your benefit, I once again draw, this is lambda p, this is upper laser level, this is lower laser level, and this is the transition which gives out light at wavelength lambda L, and this is the ground, where initially all the dopant species reside, and this pump actually excites them to the upper laser level, of course, through the pump. So as this traverses down it, they are excited, and they then would emit. Once they're here, they have come, they have been excited to this, then they will emit their spontaneously emitted photons, which will travel in all directions. Those which would shine the core clad interface at an angle exceeding the critical angle, will be able to guide it through this, and the stimulated emission will be seeded by those photons. And that is how the amplification of light will occur at this one, through stimulated emission. The central circular twist that you see here on the fiber, seen in this figure, basically emphasizes that the active length here usually far exceeds the cavity length. You see, normally, as you know, the fiber laser, the active length can be several meters to even several kilometers. Now, obviously, you cannot have a cavity, the length of the cavity which should be in kilometer. It is impractical to place the two mirrors of the cavity kilometers apart. So actually, fiber is therefore coiled so that the whole apparatus fits into a conveniently sized enclosure. So coil the fiber, and it doesn't matter. Light travels through it still without any spillage, because always it is traveling through this zigzag path. It doesn't matter what is the shape of this optical fiber. You can easily coil it, and that is what is done to fit it into a conveniently sized enclosure. And the ends of the fiber are anti-reflection coated to avoid intracavity loss through Fresnel reflection. So as you know, Fresnel reflection is actually about 4% reflection. Every time light shines onto a glass interface, it will 4% of that light will be reflected. So suppose if you don't coat this end, anti-reflection coating, then the light that will, let us say, see in a to and fro journey, light starts from here, it starts its journey, here it will undergo 4% reflection loss, then it travels into the rear mirror and it comes back, and again it undergoes 4% reflection, then it goes here, it again undergoes 4% reflection, it again travels and undergo reflection on this output mirror, and as it travels back, it undergoes again 4% reflection, then it returns back here. So one to and fro journey, it undergoes approximately 16% loss. With such a big loss, it will be a very great disadvantage as far as the operation of the laser is concerned. So you actually coat it, anti-reflection coating. You already have studied how do you coat a surface anti-reflection. Put an anti-reflection coating on a surface. So with anti-reflection coating, this loss will be reduced almost to zero. So then this is a very qualitative description of how would you operate a fiber laser. And to enhance the pumping efficiency, you actually pump it from both ends of the fiber. Just same arrangement you also put on the other end, so that you actually pump it from both ends to enhance the efficiency of pumping and eventually to get a better performance of the laser. Now, how do you scale up the fiber laser power? What are the problems and what are the remedies? Let us quickly discuss them. You see, for any laser, power scaling of the fiber laser should be like any other laser. The power scaling of the fiber laser should also be possible to increase the active length. If you increase the active length, that means you are increasing the number of light emitting species. So you will generate more light. So that is a very convenient way of increasing the power of the laser. However, this is not entirely true for a fiber laser. As with increasing power, certain nonlinear process becomes operative and eat away the intracavity power. What are they? The very long and thin geometry of the fiber has of course granted this laser two major advantages. One, of course, is easy removal of waste heat, because if you increase the surface area, the heat will be dissipated more efficiently through this large surface area. An inbuilt capability to operate on the lowest order transverse mode, or TM0 mode. And because the area is very small, it intrinsically offers advantage to the operation of lower order mode, which is called TM0 mode. These are very low divergent modes, because the area itself is very, very narrow, and it suppresses the higher order transverse modes, which divergence is higher. So this lower order transverse mode essentially makes the spatial quality of the output emitted by the fiber laser excellent spatial quality. So these are the two advantages of very long and narrow fiber. However, as the fiber has a very narrow core, an increase in power, if you increase the power, then intracavity power, that is the power that is confined inside the fiber, the power density increases per unit area, the power also will be higher. And as we increase the power density will be even more. And if the power density is more, that is the intensity is more, the electric field associated with the light also will be more. So an increase in power also greatly raises the intracavity optical power density, and in turn the associated electric field. With increasing power, the field can reach values high enough to set in various nonlinear processes that basically convert laser light into other wavelengths. Let me just elaborate a little. You see, there are certain materials which are called, it's the advent of laser has given rise has given rise to some new, opened up some new field of optics called nonlinear optics. So there are some material called nonlinear material through which, when light passes, and if the intensity of light, that is the electric field associated light, is extremely high, then they actually convert this light. Suppose this light is at a wavelength of lambda 0, or say frequency nu 0. Then this nonlinearity that is induced by large high electric field associated with this optical wave can actually convert this wavelength into half this wavelength. That is, if this wavelength were lambda 0, as it traverses through this material, its wavelength becomes half. Lambda 0 by 2. That is, frequency becomes two times mu 0, the original frequency. This is called second harmonic generation. That is, this nonlinearity doubles the frequency of the light. So these are some nonlinear processes. There are many nonlinear processes. This is one of the most important nonlinear processes. So if the electric field becomes very high, it actually induces such nonlinearity into that optical fiber. That is also a nonlinear substance. And its nonlinearity, it shows its nonlinearity at very high electrical field, which is reached when you tend to increase the power, and so intracavity power density increases, and it actually induces various nonlinear processes that basically converts laser light into other wavelengths, as I just explained. So this is a loss. To this, the energy is lost through some other conversion of some wave light at some other wavelength to which you have no interest for some particular application that you are interested in. Thus, any attempt to increase laser power, increasing the length of the fiber, will be counterproductive, as part of the laser light will be lost to the inevitable optical processes. So in a nutshell then, although a narrow fiber facilitates the removal of waste heat, it also has a detrimental effect to the power achievable from the fiber. What is that? We just discussed it. The remedy, of course, will be to put a check on the occurrence of nonlinear phenomena by reducing the intracavity power density. If we can reduce the intracavity power density, then of course we can actually put a check on the nonlinear process, which occurs at very high electric field associated with the light wave. This can be readily achieved by raising the diameter of the core. If we increase the diameter of the core, if it were say x millimeter, we make it 2x millimeter. So then the area becomes 4 times more. So the power density becomes 4 times less. Accordingly, field also will be accordingly less. Although at the expense of the spatial quality of the laser beam, as a wider core now will support higher order transverse mode. As you increase the diameter of the core, the core also supports the higher order transverse mode. That is the modes which have higher divergence. That is, you degrade the spatial quality of the output given by this fiber laser. So then, you increase the power, suppress the nonlinear effect, but at the same time, you degrade the spatial quality of the beam. Let us see if there is a solution. The obvious question that arises here is whether the higher order modes can be suppressed in a wide aperture fiber laser to preserve the spatial quality of its emission. Is it possible to increase the core diameter and yet do not allow it to support higher order modes, that is, degrade the spatial quality of the output beam of this laser? Popular technique to this end has been to exploit the bending loss of a fiber to an advantage, subdue the higher order mode. It has been found that when a fiber bends, the loss introduced is more for the higher order modes and less for the lower order modes. And therefore, if you can coil the fiber, and coiling the fiber, as we just saw, is very essential. So it is inbuilt coiling. And as you coil the fiber, it introduces more loss to the higher order modes. And therefore, you can actually almost endlessly increase the output power from a fiber laser without degrading its spatial quality. And as we know that the output power of the fiber has been reached to tens of kilowatt continuous power and megawatt scale pulse power. All right, so this is all about fiber laser. Let us quickly take a look at the performance of this fiber as an amplifier. Similar to any optical amplifier, an active fiber can also be amplified, can also amplify light of frequency that falls within its gain bandwidth. Suppose you have an active medium in which you have imparted gain, you have created population immersion, you have imparted gain over a frequency or the wavelength range, say lambda 1 to lambda 2. Now if you, so you have created gain over these wavelengths. Now if you put a beam of light to this weak beam of light of say wavelength say lambda 0, which lies somewhere in between lambda 0 at wavelength. Now if it travels through this amplifier, it will be amplified. It will extract energy. You already have studied optical amplifier. So a fiber too can perform as an amplifier. An erbium doped fiber amplifier is most popular because it actually is used as a light amplifier for optical fiber communication. We'll just come to this in a while. Erbium has a strong absorption at 980 nanometer wavelength. So how the fiber amplifier will work? It is almost the same the way a fiber laser works, only you do not have a cavity here. So the diode laser that operates at 980 nanometer, this fiber is doped with erbium. And it is pumped very well by this 980 nanometer. And the gain occurs within this region 1520 to 1570 nanometer for erbium. The 980 nanometer photons from the diode laser excite the erbium ions to a higher energy state, from where they drop down to the metastable state and get stuck there. In turn, gain builds up across 1520 to 1570 nanometer wavelength. The ability of erbium doped fiber to amplify light at 1550 nanometer, where glass fibers are practically lossless, has profoundly impacted the fiber optics communication system. Let me very quickly explain to you that. See, in optical fiber communication, long distance optical fiber communication, so this is your optical fiber. So going under the Atlantic, say to 10,000 kilometers long. Now, the semiconductor laser emits at 1550 nanometer. At this glass offers almost negligible absorption. So the data stream that this semiconductor laser emission carries, it enters the fiber at this end. And although the absorption is negligible, but it is not zero. It has some finite value, however small. Therefore, as it travels say hundreds of kilometers, it gets absorbed. It accumulates the absorption, and the signal becomes too weak. It's so weak that it cannot carry. Suppose when the signal was like this, and after traveling say some hundreds of kilometers, it has become very weak. So here actually you put this amplifier, this fiber amplifier. So at this point you amplify the light. 1550 nanometer would be our input. So this, at this point, it has become too weak, this. So this then would go into this fiber. You put it here. This thing comes here. And this gets into the fiber. And the other end, it is amplified. The other end, it is again like this. And then you have your next stage. So then this goes into this fiber. And here again, after about 500 kilometers, it falls down again to this level. So again you put another amplifier, and so on and so forth. So if every 500 kilometer you have this booster stage, and this is light to light amplification. The 1550 nanometer light, which is used for communication, can also be directly amplified in this. So before the advent of this fiber amplifier by David Pine and his group at Southampton University in England, this is to be done, this boosting is to be done. So this light, weak light, then would be converted into light, will be converted into electrical signal, then the electrical signal would be amplified in conventional electronic amplifiers, and after amplification it will be again converted back to light, and then it will put into the next stage of the fiber. So this light to electric to light conversion actually was a very complex and cumbersome system, and it actually was a main hindrance for long distance optical communication. But the advent of fiber amplifier actually solved this problem. It was actually a game changer. And today we have all light optical fiber communication network that is the backbone of today's global communication. I think I'll stop here now, and you have got a fairly good idea of what is a fiber laser and also what is a fiber amplifier.